and good afternoon to all of you, and welcome to the Smart Grid Educational Series seminar live from TUV Rhineland in Pleasanton, California. I am pleased to be with you, and we are going to be going through quite a lot of material today. So I ask you to be patient as we go through it. It may take a little bit more than an hour for me to cover this, but I think it's going to be very valuable to you, whether you are involved in technology or you're involved in business process or you're involved in policy making, whether you are a utility or a vendor or an integrator or academia, or whether you're in a national lab. I've thought of all the stakeholder groups that NIST identified in the Smart Grid Interoperability Roadmap project and thought, how could I put a presentation together that would be valuable to all the stakeholders, will go into enough depth to pique the interest of those who are technical, but remaining general enough that the layperson could also understand and appreciate. The agenda includes covering some basics about AC grid, and then I'll get into the direct current type grids. There are a lot of high voltage direct current lines being put, and I'll explain a little bit about the science and engineering behind that. Then I'm going to get into electromagnetic wave properties. I will pick up from the last presentation I made with Maxwell's equations and head in the direction of what constitutes as properties of these waves, how they propagate, how do they reflect and attenuate, and so on. Then I'll talk a little bit about the electromagnetic spectrum. I think quite often people hear bits and pieces of the electromagnetic spectrum, but have never really looked at it in totality, so they don't know the relative positioning of various applications that they come across. Then I will talk a little bit about electromagnetic wave superposition. How do waves interact with each other, both constructively and destructively? And that's when I get into the electromagnetic wave interference concept. I will also talk about the path loss. I think it's very important as we deploy all these smart meters that have radios that are producing signals of certain strength, to have an understanding of what happens as you go away from that source. Then I'll get into how electromagnetic waves propagate in different types of physical media. We hear things like fiber and twisted pair and Cat5, so I'll talk a little bit about each of those and how these waves travel. And then I'll talk a little bit about how encoding, data encoding occurs. You can have digital information that can be encoded in analog waves and in digital waves also, and I will talk a little bit about both. Then I will talk about the channel capacity. How many bits can you send in a certain pipe that has electromagnetic waves of a certain bandwidth? And there's an interesting logarithmic relationship that you should be aware of. Continuing the agenda, I will talk about the OSI stack, the 7-layer protocol architectural model that you have come across, but I'll get a little bit into how this stack actually works. We hear about it, we hear there are 7 layers, but a lot of diagrams that we see in the industry are flat. So I'm going to give you an appreciation of the different layers and what they mean. Then I'll get into the Gridwise Architecture Council architectural model, because this model goes beyond technology, gets into business process and organization, and then eventually even into policy. So you have to see all these layers and understand where the various standards lie relative to the stack. Moving along, then I'll get into the 3 critical aspects. There's the SCADA, which controls and collects data from field equipment. There's energy management, where you turn things on and off to regulate how much energy is being used. And then there is also the communications aspect of it. How does data actually travel, and how much bandwidth there is, and so on. So those aspects I wanted to cover across all the ecosystem of the electric grid, starting from the transmission and substation down through distribution into end use, but not just end use in residential, but also look at commercial and industrial. And then talk a little bit about how home plug and Zigbee are being implemented in residential setups. Then there'll be a little brief on the educational series, the next one that we'll be doing, and then we'll open it up for Q&A and discussion. So as you can see, it is a very full agenda, and I'm going to be going through it rather quickly because there are going to be a lot of pictures that you're going to see. And I just want you to get visually oriented with the electric grid. You hear a bunch of terms, and then you see a bunch of pictures, but you've never brought them together. So this is everything you wanted to know about the electric grid, but were afraid to ask. Let's get into the AC current power grid basics. So we're going to go over what the grid looks like. We're going to talk about the voltage levels and how the layout is. Then I'm going to get into a little detail from generation through transmission, through the power substation, into the distribution network, all the way to the residence. So that's the purpose of the first section of my presentation. Here is a nice little pictorial that I got from the internet that puts the entire ecosystem in a nice cartoon diagram. And you can see the power plant, you can see the transmission substation where the voltage is ramped up. You see the transmission lines carrying it to a power substation where there's a switch tower and there's a transformer, and then there's a distribution bus there, and then the voltage is stepped down with that transformer and then brought over the distribution lines to the transformer drum that is outside your house, where then it is brought down further to 240 volts, which is introduced in your house. You can get 2 parts of 120, or you can get 240, depending on what type of appliance you want connected. Here is a diagram that I've shown you in a previous presentation, but I think it's good to give you an idea that the power plant will produce voltages on the order of a few thousand volts. And then it's stepped up in the transmission substation to anywhere from 100 kV to 765 kV. And those lines, transmission lines, carry this to a power substation, and then at the power substation, you bring the voltage down to the level that customers need. Now, some customers, like industrial customers, will require high voltages for welding, for various types of power tools, so they don't want to wait for 240 volts. So you can see in this diagram that they're getting higher. So they could be connected directly to a substation. They don't need to go through a distribution network to tap the electricity. Others, like residences that have lower voltage requirements, are further down on this diagram. Let's talk a little bit about generation. We hear that, we have over 1,000 gigawatt electric grid, and that electricity is produced by a variety of different sources of energy. Here are some of them, and there's like a geographical layout. At the moment, we have maybe about in the mid-40% for coal generation, and then it's coming down because renewable energy is growing and natural gas is growing. Nuclear is around 19%, hydro is about 7%, but natural gas is growing very rapidly, so I would say it's in the mid to high teens now. And then you have solar and wind and other things in the mix. But it gives you an idea. And you can see the distribution, and it makes sense based on where the resource is, and also what the local politics may be, and about their desire for clean energy one place, jobs in another place, labor wages in another place. You can see that where the type of source of energy is very labor intensive, you see that the wages may be lower there, so the companies can afford to have those types of plants. So there's a lot of economics and sociology and politics involved in how this is distributed. let's take an example of what happens in generation. Again, we had this diagram on the right side with the 3 coils and a rotating magnet. That's how electricity is produced. So the thing in the middle is the thing that is connected to a shaft that is connected to the turbine, which may be in a steam cycle of a nuclear power plant, or the steam cycle of a coal plant, or it could be the water flowing through an inlet and moving a turbine, as in a hydro plant, and a natural gas also with a steam cycle. It could be the wind turbine turning the shaft, which is producing this electricity. So all of these sources of electricity cause this magnet in the middle to be rotated. This magnet is actually an electromagnet. It has a DC current running through a loop that creates a magnetic field, and when the turbine turns and that loop turns, it cuts the magnetic lines of flux that this loop creates, cuts these coils, these 3 coils that you're seeing 120 degrees apart. So as a result, electricity is generated by Faraday's law of induction in all 3 of these coils, and those are the 3 phases that we carry out from a plant. Everywhere in the United States, this is happening in a plant. And the reason why we pick 3 and not 2 or 4 is that when you do 2, you have multiple times when the voltage goes to 0 if you have 2 phases. In a cycle, just think how often you'll hit a signal going to 0. If you go to 4, you don't really add much in terms of continuity of power. You know, the marginal utility of adding an extra coil is less. You see how these 3 voltages in this diagram are phased 120 degrees apart? So there's always a peak coming up. And this is very good because if you provide 3-phase power to high-end applications in industry, what you get is continual power, which some power tools really need. So we found an optimal way that provides as continuous a power as possible without being too cumbersome or expensive by putting too many coils. That's why the sweet spot was 3. So just keep that in mind. Why isn't it 4-phase or 2-phase? So with this 120-degree out-of-phase, 3 sources are being now carried on the transmission line. Let's look at the next diagram. This is the transmission substation, and it typically is co-located with a major power plant. This is where the step-up transformer is that takes you from a few thousand volts to hundreds of thousands of volts. The lines, the transmission lines that you see here, you will see 3 major pairs, and then you will see ground. The ground is the line that is running on the top of the tower. And sometimes you'll have multiple, as in this case, you'll have multiple wires, so you may have 2 sources that are carrying electricity, because it's very hard to get right-of-way in transmission lines. So they try to put as much as possible once they get a corridor. They try to carry as much electricity as possible. And as I'll get into it later, AC currents are a little fickle. You know, they have skin effects and things like that. So there is less than optimal transmission of electricity. And that's when I'll show you the benefits of high voltage direct current also, and how it can overcome things like the skin effect. But here we have a very nice picture of things that you see. If you're in the Bay Area and you go to Automall Parkway exits between 880 and 680, you'll see this. I'm sure wherever you are on the internet today, on this webcast, you will see a transmission line like this somewhere near you. This is how bulk electricity is carried from the plant to an area where it needs to be distributed. Now we get to a power substation. Here's a panoramic view. We see this, we go past it. There's a fence around it, but there's usually some commercial area where we're going, which it's next to, so we don't pay attention to it. But I think there's one in Fremont by Fry's Electronics. There's like this big substation there. So this is an example of a substation. It has specific components which are important. Notice I'm not talking smart grid right now. I'm just talking about a regular old grid. I haven't spoken about anything really electronic yet. It's all mostly electromechanical stuff. So we have a switch tower The switch tower is on the left of this diagram. You see the structure, and then there's a transformer in front of it, and then on the far end, you have the distribution bus with the voltage regulators. And then from there, you're connected to the distribution line. Now I'm going to magnify and go a little deeper so you understand the components. So here's the switch tower on the left, and you can see the transmission lines coming in and feeding into the switch tower. Why is the switch tower there? The switch tower is there so that it can disconnect the transmission line from the power substation if there's a need. The switch tower has the switches to do that. The transformer will take you down from hundreds of thousands of kilovolts to a few thousand kilovolts. I'm sorry, let me say that again. A few 100,000 volts down to a few thousand volts. That's what the purpose of the transformer is. In some cases, depending on what the application is, they may not bring it down as far as is needed for residential, for instance, and I showed that to you in a previous diagram. So you have the switch tower, you have the transformer, and you have the transmission line. Now let's go further, and we get to the distribution bus where the voltage regulators are, and from the right of this, as you can see, the distribution lines now are connected to this distribution bus, and you see the two towers on the left side with cables running in opposite directions. The cables in between the poles are just meant for support. And then you have left and right cables that actually carry the electricity out onto the distribution network. Now we are in the thousands of volts going out of here, as opposed to hundreds of thousands of volts. Let's go a little further. Now you see the magnification, and you see those support wires between the two poles on the left, and then you see the power lines actually carrying in opposite directions, left and right, the electricity out of the power substation. And then the diagram on the right shows a typical scene that you may see if you go on a country road or in the city as you go away from a major substation. And again, you see 4 wires there. 3 of the wires are for the 3 phases of electricity, and the 4th wire, usually running on the top, is the ground wire. Here's a voltage regulator that makes sure that the voltage levels are right. Sometimes the voltage can sag, and sometimes it can be higher. And these cylinders that you see on the left adjust the voltage. What you see in the middle diagram is a tap. Here, if you have a situation where you have 3 phases and you want to take it down on a street on 2 phases, you'll put taps. And that's why you see the wires going to the right are only 2, with the ground being the 3rd, and 4 are coming with 1 of them being ground and 3 being the 3 phases. So here in the middle diagram is a typical tap going from 3 to 2, and then the diagram on the right is a 2 to 1 tower. So you have 2 phases coming in and only 1 going. So typically, when it's 1 going, as you're seeing to the right in the rightmost diagram, it's going to a residential street. So this is the kind of handoff that is occurring. So as you can see, we start out very high, and then we slowly work our way down. And as we're getting closer to the residence, all we need is 1 phase from that transformer. Okay, moving along, now you see the actual pole that may be sitting outside your house. There's this drum, it has a transformer in it, and what this transformer does is it converts the 7,200 volts that typically is sent from the power substation down to 240 volts. And that's the wire that you see on the right-hand side, the diagram on the right, going to the house. Now I'm going to show you the voltage and how it works. So you see how you have a primary coil at 7,200 volts and then a secondary coil that brings it to 240. You tap it in the middle and you get 120. They're out of phase, 180 degrees out of phase. That's how they add up to get you the 240 volts. So their signals are 180 degrees out of phase. So every time in the middle, when you have a crest of one, you have the trough of the other. So the delta between them is 240. So this is how you get electricity in the house. So you have some appliances where you put it on the two ends, and then you get the 240 volts, or if you tap it in the middle of the transformer, you get the 120. So every house, at least as I understand it in North America, has this possibility. So if you have a washing machine or any kind of high-power device, that may require 240 volts. And then the typical voltage in the house that's coming to the wall is 110. But this is how they break it up. We have, yes?
I was saying, how come in Europe they just use straight 220 or 240? They don't break it up?
Oh, I think it's, the question was that how is it that in Europe they use just 240 and they don't break it up into 110? I think it's just tradition. I see that, for a given amount of power, there's less current over there because it's voltage times current. So the devices use less current than they do in the U.S. But on the other hand, it may be more dangerous in another way in terms of getting the shock. And 110 is a lower shock.
Just keep the wire size down.
Yeah, and keeping the wire size down. Yes. Yes, because of the current, the amount of current will draw. The diagram on the right-hand side shows you the typical panel, the switch panel in the house. Switches are very important because often, as part of living, we may have a hot wire touching ground. Just because a squirrel might cut into it, or you're vacuuming and the wires get cut, all kinds of things happen in life where hot wires touch ground. Now, if you didn't have a switch, basically whatever is making the contact is where all the current will keep going until it catches fire because of the ohmic heating. So you have to be very careful. So instead of putting fuses that just blow up and then you have to go replace it, switches are a more elegant way of dealing with it because the switch will just open, and then when the short is restored or is fixed, then the switch can be put back. And you see that in a house, that if you try to force the switch to go, it'll just not go until that appliance is removed or a bunch of appliances. So I'll give you an example. In our house, in our kitchen, if I put on the electric heater to make tea for hot water, and if I turn the microwave on and the toaster on, it's too much for my panel. And then the switch goes off. So we're only allowed 2 out of 3 at a time. And we learned that the hard way. Let's now get into direct current, because alternating current has been there for many, many years, and we rely on it for the transmission, distribution, and consumption of electricity. But there are some real benefits that direct current provides. These are examples of 2 HVDC lines. They are 2 of the largest in the world, and I'll talk a little bit about North America in just a minute. But here is an example of how much power can be carried on these very, very simple cables. And the nice thing about DC is that when you have alternating current and alternating voltage that goes with it, you have a situation where the peak voltage, let's say you have 110 volts. That 110 volts is the root mean square voltage. So the actual peak that goes with that is about 170 volts. So the issue is that power is transmitted on AC lines based on root mean square voltage, not peak voltage. So you've got a peak of 170, but net, it's as if you only had 110. So if you had DC, you could actually carry the power all the way up to 170 volts. So if voltage times current, if you think about that product as power, you have about 41% more capacity to carry power on the DC line compared to the AC, because you can run it at peak, as opposed to AC, which gives you only net root mean square of the peak. So that's the 0.707 point. So if 170 is the peak, 0.707 is the 110 volts. So because of that, it's more efficient to carry electricity on DC than it is on AC. In addition, there's this concept of skin currents. What happens is that currents don't travel very uniformly in AC because of the skin effect that occurs on the conductor. And this is also a result of electromagnetism and Maxwell's equations and how the charge will carry on the conductor. So a result is that you have to have bigger and thicker wires for AC transmission than DC because you need more surface area to carry the same amount of current. That adds to the cost. However, to offset that, converters, which are mostly based on solid state for DC to rectify from AC to DC, the challenge is there's a cost associated with those converters. So they've done studies, trade-off studies between AC and DC, and they found some sweet spots that if the transmission line is beyond a certain length, the cost of conducting exceeds the difference in cost of the conversion.
Then you have the
in those situations,
you also have the, I think one of
yes,
the
and then there's the capacitive
losses, you know, the inductive losses.
Inductive losses are there, and also there's a capacitive current, and it will eat up, it's a parasitic loss on the AC line. So for all of those reasons, they found that there are certain thresholds of distance beyond which DC outweighs AC in terms of overall cost for carrying a certain amount of power. The other good thing is the geometry gets a lot simpler. So when you have more capacity to carry current, the tower size gets smaller, and that also helps reduce the cost. My prediction is that given the growth in electronics, this cost of the converter is going to keep coming down, and it will become more and more feasible to have shorter distances in which you could do direct current. There are other benefits. For instance, you could have two grids, AC grids, that are out of sync. Their clocking mechanism is not together. And you can put a DC line between them, and it acts as a big storage, basically. So here again, you can transfer power between two unsynchronized AC systems with a DC line. You can also have a very good way, for instance, if you have large solar farms, it's already producing DC, you put that on the bus, step it up, run it on the DC line, and then have it converted somewhere else. So there are many, many benefits of DC, and I would really encourage you, if you're interested in this area, to delve into it more and see what are some of the technological breakthroughs that are coming in the conversion process from AC to DC. Here's an example of two AC grids that are connected with a DC. This could very well be ERCOT with the southeastern part of the grid, or MISO and the northeast. All the 5 or 6 sections in North America, the autonomous zones, are connected with DC lines like this. And that allows you to maintain stability without requiring synchronization between them. Here are some initial HVDC lines that have been established in North America, and it's a simple diagram, but it shows you that it's becoming more and more popular. And I think that as wind and solar become big, and the pressure will be on the transmission lines for AC systems, you'll see more and more of this as the cost comes down.
But I remember reading recently that one of the early, I think it was Westinghouse, that started DC lines in New York.
Yes.
There were some systems that were still using DC up until just a few short years ago, and they just removed them.
Yeah.
So it's actually contrary to what you're saying.
Yeah.
Here.
The first major DC line was Bazaar in South Africa, from the Bazaar then on the Zambezi River to South Africa, which is about 1,000 kilometers. And one of the reasons they put it there is those long distances, the inductive losses become overwhelming. You know, whereas the ohmic losses, obviously, just a question of voltage, right? But
I think the key thing to think about, Mike, the question was that, there were some DC lines that were removed. It's not DC in itself. You have to look at the entire system and think of the conversion process and the quality of the conductor. All of those things are important when you evaluate whether you want to keep a system or not. I'm speaking now in generalities, that when you're thinking of building an AC system or a DC system, look at the distance, look at the overall cost and what your power requirements are, and based on that, make an objective decision. Don't be an ideologue when it comes to AC or DC. I think that maybe that rock group should come back. I think because AC and DC will both be accepted. All right. Because I think they were way ahead of their time when they built that AC-DC rock group. Okay, here is an example of a diagram of a house that could be off-grid and it could be DC-based. Look, solar already is producing DC directly. That's the silicon chip effect. And then you have a wind generator that's producing AC, but you could store that energy in a battery and then supply it as DC to the house. This can really simplify the wiring in the house, by the way. And it can reduce the overall parasitic losses. So you could have a very clean copper running DC in the house, so your ohmic losses are very low. You can avoid the conversion, twice conversion. You only convert once from AC to DC for the wind. Because ultimately, if you look at electronics in the house, again, it requires DC voltage. So you're going to AC and then you're converting again to DC in the devices itself. So if there were a new class of appliances built that were DC to begin with and not have AC, you could have a very efficient house, and you could simplify the wiring, and you could reduce cost. But it's going to take a while. This is a vision of the future.
I heard there's another disadvantage to using DC in the home is that there's a higher incidence of corrosion because the AC, because it alternates the current, it prevents the corrosive effect that's caused by acids. Electrolysis, exactly. Prevents electrolysis. And DC actually can cause more corrosion due to electrolysis.
Okay. So the point was made that the presence of direct current on copper can cause corrosion because of the electrolysis. Yeah, and these things have to be looked at, and there's a whole research going on materials and stability. I mean, I know that as a result of the stimulus funding, there were a lot of projects that are being done with high temperature superconducting coils, to reduce the amount of loss. I believe American Electric Power was doing some tests like that. So there'll always be research going on to improve materials. But what I'm suggesting is that we think of all the dimensions, some that Mike has brought up, and think about the converter costs and the maintenance costs. All of that needs to be looked at. And this is where engineering is so exciting. I mean, I never would say that, but engineering can actually be very, very exciting.
This is a fact of life today, just off the grid in Belmont, Nevada, where all the houses have both wind and solar, and it's a mecca for amateur radio operators because it doesn't make much noise.
The induction loss, there's no induction.
The inverters, they have to be snubbed.
Okay, so the point was made that there's a place in Nevada, Belmont, Nevada, where there's solar and wind both, and it's a very good place to be radio-free, so which would allow you to test for cons. But I got to keep moving. All right, so coming back, now I want to get into electromagnetic waves and its properties and how we're going to carry data and how are we going to manage the grid. I gave you these Maxwell equations in both point form and integral form last time. I'm going to pick the top two, the Ampere's law and the Faraday's law, and by doing a curl on both of those, which I did last time, I can come up with this equation that you see, which shows that the Laplacian of the magnetic field strength, del squared B, is equal to 1 over c squared, and the second time derivative of B. So here's a spatial derivative on the left and a time derivative on the right that are equated for magnetic field. And the same can be produced by doing the curl of E. You get the Laplacian of E and 1 over c squared, and the second time derivative of E with respect to time. Whenever you have a spatial and a time derivative, second order, equated like this, solutions of the kinds that are sines and cosines by Euler's equation, e to the I k r plus minus omega t plus phi, reduces to sines and cosines, and that's what this is. Now, k is the wavelength number. It's 2 pi over lambda. And omega is the angular frequency, 2 pi f. So what you really have is a dispersion relation here. A dispersion relation is a relationship between k and omega in space. And as it propagates, there will be interplay between the k and the omega. And these equations create that. So that's how you can, it's a parabolic equation in time. You can do finite difference or finite element, and you can build the wave into the future using a computer. So this is how waves propagate. I wanted to give you the basis of it so you can see why these waves are polarized 90 degrees apart. You see how the electric field is pumping the magnetic field and the magnetic field is pumping the electric field. So it's like this choo-choo train. I think I can, and it can go actually through a vacuum. Think about this. There's no particles. Just sit for a minute and think about this. There's displacement in a vacuum. What does that mean? I mean, like sound waves, you know, you see molecules vibrating, touching another one. It makes physical sense. We can touch, feel. What are we talking about in a vacuum? There's induction going on of electric and magnetic fields with no particles. This is a miracle. And this is, Maxwell couldn't figure this out, by the way. And this is why he couldn't discover the photoelectric effect, because he kept thinking there was some ether that was carrying it. Today we know that mu0 and epsilon0, permeability and permittivity of free space, means free space, no material. Keep that in mind. This is a miracle. And this is, you know, for me, it's a spiritual experience when I see something like this, that it's something that we cannot connect with in our day-to-day lives. This is beyond our experience, and yet it's there. Every time you turn a radio on, every time you see the sun, this is happening. There's a vacuum between the sun and the earth, and yet it pumps and comes. All right, I'll get off my Maxwell theory soapbox now. Here are some properties of the wave. You have a wavelength, which is the distance between two consecutive troughs or two consecutive crests. And you have an amplitude, which is the distance from the peak to the middle point. And there is a certain speed at which electromagnetic waves travel. They travel at the speed of light. It's 3 × 10⁸ meters per second. So you have all these properties that go with a wave that travel. And the way it travels is governed by Maxwell's equations. Here we have the electromagnetic spectrum. This is kind of like the periodic table of wavelength. Think about it. Everything that you experience from the moment you wake up till you go to sleep that involves electronics and communications is right here. You see stuff, it's in the visible spectrum. You go for a massage for your leg, it's in the infrared. You turn on your microwave oven, it's right there, 2.4 gigahertz. Everything you experience, you go for an X-ray because you broke your bone, it's there. It's all in a continuum. And it's all based on that Maxwell's equation. What an amazing unifying force that's bringing your entire human experience on one spectrum. So don't think of this as a bunch of separate things. It's a continuum. And in different bands along this spectrum, we have different experiences. Everything from the voltage that's being carried on the wire at 60 hertz to long wavelength radio waves, to infrared, to the visible spectrum, to ultraviolet, and then going beyond to X-rays and cosmic rays and all of that. Now, if you look, the left side says non-ionizing and the right says ionizing. So you know ionizing means more painful. There's more energy, and it will dig into you, and it will cause displacement of charge. So that's why nuclear radiation is so dangerous, because it's in the ionizing side. And the non-ionizing side means that the material stays intact.
The ionizing is a function of the frequency, the Planck constant, right?
Yes. Yes, so there's a threshold because of quantum effects.
You don't have the quantum energy, to displace
exactly.
it, so.
Exactly. So the point is being made that there's a quantum effect. There's a certain valence electron that requires a certain amount of energy to get out and become part of the conduction band or become a free electron. And that requires a certain amount of energy. And if you take the equation that relates Planck's constant with speed of light and energy, there's a certain energy that's needed to get it out, and that energy is related to a frequency and a wavelength. Wonderful. Moving right along, here is an example of interference of two kinds. You can have two waves, and they follow the law of superposition. So if two waves are perfectly synchronized, they'll add. And if they're out of sync, as in the case on the right side, they will cancel each other out. So if you heard of these white noise type devices or the headphones you get for the plane, they do a Fourier analysis of typical noises, and then they'll generate a noise in the opposite direction to cancel the noise that you're getting from the ambient. And the more you pay for the headphone, the deeper the Fourier analysis was. So that's how you pay. Every $100 you pay for the headphone, they sat in the lab longer to figure it out. Okay? There is no real magic going on. It's all empirical evidence. And diversity also of different sources. Here is a signal-to-noise ratio, a formula that is important to understand. So here is a diagram of someone who's generating a certain amount of signal from the left side, that's the human being hitting something, and then someone further away is generating noise, which is going through a diffuser to spread it out over a wider area. And so you see at the 45 dBA level, there's a background noise. And now you can see the function, that orange line shows you the graph of the power. And see how it's dropping as you go away from the source of the signal? At one point, it'll be hard to discern it because the ambient noise is so high. But at this point where they're showing with the arrow, you get about a 2 dB signal-to-noise ratio because the actual value of the signal is 47 dB and the background noise is 45, so the difference between the two is 2 dB. This is very important, especially when you're doing home area networks and any kind of building automation system, that you have to be cognizant of the noise. And if the noise is significant and you go so far that the signal drops, that the signal-to-noise ratio is not that much, you may not be able to carry bits in it, and you may not be able to convert it into meaningful signal on the receiving end. And I will show you that in the next diagram. Here we have a path loss as a function of distance. The L is the path loss in decibels, and the D is the distance between the transmit and receiver, and lambda is the wavelength. This is a very good formula to see why high-frequency broadband signals have difficulty going very far, because they incur much more loss than long wavelength short frequency. See how it's a function of lambda? So if you're thinking about loss as a function of distance, so the bigger the wavelength, that means the lower the frequency, the farther you can go with less loss. And it's a square root relationship because it's 20 log, so you take 2 times 10, so you put the 2 up, it's a square relationship. So the actual range relationship is a square root relationship. This is why sub-gigahertz communication is very, very cool. You can go much farther. Yes, you get fewer bits per second, and I'll explain why in just a sec, but you get better range. So 900 megahertz is sweeter than 2.4 gigahertz. Now, the reason why 2.4 gigahertz has become the standard for a lot of home automation is because globally, 900 megahertz is not part of the open public spectrum. It's North America where the 900 megahertz is there. So to have larger market share, vendors decided to standardize on 2.4 gigs for Zigbee and other types of devices.
And they were short range.
Yes. But the problem that occurs at 2.4 gigahertz is that it interferes with microwaves, it interferes with laptops, with wireless, and that reduces your signal-to-noise ratio, and then you can't carry as much data. So you can argue back and say, well, energy management doesn't require too many bits. Agreed. But if, let's say, a situation is there where a demand response signal needs to get to appliances to turn off at a certain time, and just at that time the signal-to-noise ratio is low, and that signal doesn't go, suddenly it can be destabilizing for your grid. So the idea is to have link margin. Link margin means have enough dBs around so that even if the noise is high, there's still enough cushion to carry the data. Because as we move to renewable energy, and we rely on demand response more and more for grid stability, we cannot play games in the house. The house becomes a critical part of the infrastructure. And so that's where standards are important, certification is important against those standards, and making sure that there is enough link margin, there's enough redundancy, so that typical noise will not block it out. Let's now talk a little bit about the various types of media in which we carry information. Wireless is pretty straightforward. You have an electromagnetic wave, you modulate it in some way and you hold data. And I'm going to talk about those modulation schemes in just a minute. And then the other one is fiber. In fiber, you have photons, light, carrying the data. So you have very, very high frequency. So you have lots of bandwidth. And you use total internal reflection in a fiber optic cable for the wave just to keep going down, and you can actually bend it also because of the internal reflection.
Actually, they don't just modern fibers don't use total internal reflection. They use
gradation in the refractive index.
The
so
refractive index changes over the diameter of the cable. Okay.
Yeah. So we have some very technical people in the room who told me it's kind of like the atmosphere, where the density changes over the space. So it's gentler. But the idea is that it keeps it within the fiber optic, so the signal that carries at high frequency, a lot of bandwidth can carry a lot of data. And that's why FX cables, you know, you've seen TX and then FX. FX means fiber cable that can take you into gigabits per second also. And that's primarily because of the bandwidth that goes with it. I am stealing my own thunder here because there'll be a formula that'll show it to you in just a minute. Twisted pair. This is not one that needs therapy. Okay? Twisted pair just means that it's like a phone line, like a POTS, or just two wires carrying data. And a lot of serial protocols can be carried on twisted pair. You may have heard of RS-232, RS-485. Those types of protocols can be carried over this kind of thing. And plain old telephone service, POTS, that you know of. Cat5 is a little more complex. It's actually for digital communication, and it's used for Ethernet, IEEE 802.3, and it has, I believe we use 4 wires for, it has the capacity for 8.
4 pairs. Yes, 4 twisted pairs.
4 twisted pairs, yes. So, but not all the services are used.
Most often, all pairs aren't used.
Yeah. Mm-hmm. Yeah. So the point was validated that not all the pairs are used, but this is a good way of carrying digital information. Again, it can take, for instance, 10 megabits. We started out with 2 megabits per second early on, and then we moved to 10, and then we went to 100, and then we moved to gig, but gig moved into fiber optics, as I understand it, because the channel capacity is just not there. So Cat5 is a very, very popular thing for local area networking. It's that wider blue or gray wire that you see with the wide end, and it has the, you have RJ11 for telephone and RJ45 for Cat5. And then you have power line. Power line can actually run like Ethernet on the conductor in your house. If you look at the frame of a power line, a typical protocol, it looks a lot like an Ethernet, but it's just running on an electrical line. And this is really good because houses are already wired. So if you could put an adapter on either end and convert it onto a power line, and basically the disturbance carries on the electrical line, and then the adapter converts it back into digital information into a Cat5 environment or wireless or whatever the adapter will convert it. So these are some of the ways in which you can carry data. Some of it can be done analog, like twisted pair, or digital also in all the other types of media. Here are some encoding schemes. So one encoding scheme you see is the amplitude shifting that's going on. That's the first one. And the other one, the second one, is on-off keying. So basically, if you have a 1 or if you have a 0, you can see when it's 0, there's nothing going on. When there's 1, then it starts squiggling. And then when it goes back to 0, it's horizontal. So these are some schemes. The third one is frequency shift keying. These are ways in which you can put digital information into an analog way just by playing with the parameters of frequency and amplitude, and in this case, the carrier crushing it to 0 or letting it oscillate, whether it's a 0 or a 1. This is very important because there's so much stuff out there that's running this way. But you have analog waves carrying digital information. Modems work like this. All right, moving right along. Now, how about taking digital wave and carrying digital information? So we have a variety of encoding schemes. These are just samples, by the way. There are many, many more. And that's the nice thing about technology, is that we have a lot of brilliant, eccentric people who can never agree to one way of doing something. So they'll keep coming up with newer and newer ways because they'll have some logic behind it. What is the logic? Mostly about not putting charge on the wire. You know, if you like send a whole stream of 1s and keep saying 5 volts, 5 volts, after a while the wire will get charged. So it won't be as receptive to your signal anymore. There'll be a quote-unquote noise on the wire. So you have to keep, if you have 2 consecutive 1s, bring it down so that it keeps neutralizing. So those are types of logic people have used to come up with more and more complex. And I'm just giving you 3 to show you how wonderful and diverse we are as a people. I just love it. I just love it. And thank God for electronics that can interpret this and convert one to the other. It is not going to be a test at the end of this, by the way, on which one is which. But I just wanted to show this to you. I laugh every time I see this. All right, now we have a formula. This is what we've been waiting for. How about a formula that relates the channel capacity, which is in bits per second, with the bandwidth that's in hertz, and the signal-to-noise ratio? And if you look at this, then you understand why fiber has a lot of channel capacity and a dirty wire, copper wire, has very low. It all has to do with the signal-to-noise ratio. So for a given bandwidth, you can carry many more bits on fiber than you can on a dirty wire of copper, just because the S/N ratio is much higher in fiber than it is in copper because of the impurities in copper. So the cleaner the copper, the better the S/N, and that's how you saw the evolution in data communication on copper wires. As the copper got cleaner, we could run more and more bits. But then we moved to fiber, and there was a big leap in our channel capacity. So keep this formula in mind, because this formula and the path loss formula together govern a lot of what goes on in a home area network or in a building automation system that's based on wireless communication. Because those noises, those interference sources will affect S/N, and for a given bandwidth, it will really reduce your channel capacity. And if your protocol is very byte intensive, then prayer is a good option.
I'm going to have this tattooed on my arm.
Yeah.
All right.
Can we go back to the copper? How do you determine the kind of copper?
The composition of the copper. The more impurities it has.
Well, how do you? So what?
When you buy it, it'll tell you the grade.
When you spec it in. Well, so what sort of wire, copper wire, should you be specing?
So anyone who goes to Home Depot and buys copper wire, I'm not up on the grades.
Well, is there like TUV spec wire?
Oh, do we standardize on that?
Actually, we're working on TUV spec copper for solar panels, and that is essential that the copper there has a certain purity or certain characteristics. It's not a question of purity, it's a question of characteristics. And I think that's also what you're referring to.
Yes.
Because it doesn't necessarily need to be copper, it would be good if it were gold, right?
Yes, yes.
So,
yeah, any metal that has the properties where you have plenty of electrons in the conduction band to carry the signal.
So it's basically electron mobility question,
yes.
you know. So that's why I said gold, because...
Yes. But I will say that the vendors who provide wires do comply with certain standards for the cleanliness of the metal that's carrying the signal. So you don't have to worry about the material as long as you buy from a bona fide source. And there are, you know, like Annixter, and there are many, many wire companies that are established, and they do that for a living. We're good that way because this industry is old now, that these standards are there, like UL and CE and all of those standards that we're familiar with. Okay, now I want to get into the electronics part of my presentation, and we're going to run for another 15 minutes, and then I'm going to open it up for Q&A. As you can see, it is nonstop. So let's now talk about how do we do communication. Up to now, I've only been talking about electricity and magnetism and physical media and all of that. Now I'm getting into the logic and eventually into the application. So the OSI stack, the OSI stands for Open Systems Interconnect, and it's a 7-layer model that's to break up the communication problem into 7 layers. Those layers are shown to you here, and this diagram also shows you that when we are connecting two geographically separate things with some wire in between, a network of some kind, only the bottom 3 layers are involved in the intermediate devices between source and destination. And that the upper layers, the TCP layer and beyond, or the transport layer and beyond, only communicate end-to-end with each other, with their peers. So think about this stack as having relationships of each layer with the layer above it and below it, and its peer on the other side. Only the bottom 3 layers will talk to the device next that's adjacent to it, and then that will talk to the one adjacent to it, namely routers and switches, and then, of course, the wire. So every layer here has a purpose, starting with the physical layer that gives you mechanical and electrical characteristics. You have and that's where the encoding occurs. Then you have the medium access control layer, or the data link layer, which actually has 2 parts. There's a logical link control layer, LLC, and there's a MAC. The MAC sits below the LLC. And these 2 layers do things like flow control, error control. They do CRC, you know, cyclic redundancy checks to make sure that the data has integrity, and that there's flow control also, so you can do buffering and stop from flooding too much data on a line when there's too much congestion. The layer above it is the network layer. This is the technology and protocol. It's kind of like an agnostic layer that gives you a universal addressing scheme that allows you to connect between one source and one destination that are not in the same network. They could be across multiple networks. But because there's that universal addressing scheme, they'll find with routing tables a way to get from source to destination. So this is the first layer that is agnostic to the underlying technology. And then the transport layer is there, again, for making sure that there's a windowing, that the amount of data that you transmit is limited. So if there's congestion going on, you want to make sure that you throttle down. And then when things are good, then you slowly increase the window size. It also acknowledges segments, so that as data is taken from one source to destination, when you arrive at the destination, you collect these segments. When they're all ordered in a nice row, then you present it to the layer above you, namely the session layer and presentation layer and so on. So by having transport layer, you can actually guarantee throughput. And this is why TCP-based services have guaranteed throughput, but their cousin UDP, User Datagram Protocol, is connection less service, best effort, and doesn't have that guarantee. So it's like sending a letter, registered mail, and getting that signed thing coming back saying it got there. But the irony is that the acknowledgement packet comes back in a connection-less way. So you may get it or you may not get it. So best effort. But there is enough intelligence in the protocol that if it sees an acknowledgement of a higher number, it knows the lower number got there. which is a very interesting way that you can lose some acknowledgments and still continue your flow of data. You could spend a week just talking about this stack. I'm not.
Okay.
Next slide. We now have a way to show you how the data that starts from the application layer slowly gets appended with headers all the way down to the physical layer. This is very important to understand because this is all overhead. Remember, data is the only thing that's going to make a difference on the other end. The rest of it is just all the maintenance you have to do to get it over there. So this is why we've started using 6 low-pan and low-power narrow bandwidth networks, and we reduced the header, the IP header, on purpose so that the data as a function of the overall frame is a larger fraction so that the throughput goes up. Because in low-power narrow bandwidth networks, we don't have the luxury to have these long headers and block all the mesh and not get the data through. Because remember, time is of the essence when you're sending a demand response signal. That's the holy grail. Get the devices to quickly respond to changing situations. You can't be messing around with big headers and slow response times on a mesh. Now I'm going to show you some of the popular protocols at these different layers. Notice they're not all sitting at the same layer. You have to get an understanding that there are lower layer things like Ethernet. There's the middle of the stack like IP. ICMP is like ping. ARP is address resolution protocol that helps you figure out what the MAC address is if you know the IP, and IP if you know the MAC, and so on. DHCP, you all know that because you all have private networks in your house, LANs, in which you pick up the IP address from the router. Yes? Linksys, Netgear, Belkin, they all do this. TCP and UDP, I just told you about that. TCP guarantees, UDP doesn't. So FNMP data for network management is UDP based. So I think of this as dolphins and porpoises. They're cousins of each other, but they're at the same level, same type of animal. But one is guaranteed and the other one isn't. And then the upper layer services like POP and DNS and HTTP and FTP, you've seen all of these if you're in the networking IT world. If you're not, if you're just a user, you would definitely know HTTP. You may know SSH because it will create a secure shell connection to devices out in the field. You may know FTP because if it's a file that's very big, you may transfer it using the file transfer protocol. POP, you may know if you set up an email system. So you see, these are very familiar protocols. But what I wanted you to appreciate here is we don't follow the United States Constitution when it comes to these protocols. They're not all created equal. They're different, they address different issues, and they're at different layers. So when we talk about interoperability, we better be talking at the same layer with each other rather than, diagonally across. That doesn't happen. It only happens with peers or above you or below you. That's where interoperability is needed, is in the exchange of data across layers, adjacent to each other, and with their peers. Now let's get into the grid-wise architecture console model, and here we have 8 layers. And notice that the technical layers, 1, 2, 3, cover the entire OSI stack. Everything above layer 3 is above the OSI stack. So this is OSI stack plus a whole bunch of stuff. You see the information layers in the middle, that's 4 and 5. Then the organizational layers, which are 6, 7, and 8. And you can actually come up with proper processes. So semantic understanding means object models, having abstract object models, and being able to represent the attributes of different devices and know what their ranges are and what type of data it will be. Those are all part of an abstract object model. That's semantic layer. Business context, what are you doing? What's your business application? Business procedures, a particular way, and this is where use cases are going to be very important, because you have to break it down to saying what kind of transaction is going to occur. This is not a technology issue. This is at the business level what's happening. And then you have business objectives. What are the goals of the organization? How do you align IT goals with business goals? Those kinds of things. And then at the highest layer, you've got economic and regulatory policy. I have to say that the upper layers are not as developed as the lower layers are, and they are highly proprietary, I'm finding, in organizations. But the holy grail is to come to a consensus on all these layers. And then you can have true interoperability in the smart grid at all levels. This is very, very important with the fast proliferation of companies coming into the business, where a utility that was previously vertically integrated today has to deal with so many partners. If you don't have this type of interoperability at these layers, you could be stuck in manually intensive procedures ad nauseum. So that's why I highly recommend that people look into all of these layers and not just stay in the bottom technology layers. All right. We don't have too much time, but I wanted to at least show you some of the protocols that are relevant in SCADA. That means controlling equipment and collecting data from the field. In energy management, regulating devices so that the load is what you want it to be and not be too high at certain times. And then, of course, the communication protocols underneath. This is just a survey. And I will do another presentation in a couple of months where I'll do a deep technical dive into the various protocols themselves, with showing you byte headers, commands, and things like that. I think you really could benefit from that in the protocols you're interested in. But at this level, I just want to give you a lay of the land to show you what it looks like. This is what I call the mother of all pictures. So you have the GUAC stack on the left side, and then you have all the smart grid related protocols that we've been dealing with in the various priority action plans and the DUGs, the domain expert working groups of NIST. We've been dealing with them in the DHS, ICS, JWG working group. We've been dealing with them in the DOE, NESCOR project, and a variety of other projects. This is the consolidation of all of that. These are the utility-relevant protocols. And notice, again, there's a concept of layers as to where they belong. And it is very important for us to understand that they're not all equal. So you have things like DNP and 61850, which are like for field equipment and substation automation. They cover both T&D. You have things like SIM, Common Information Model for transmission and distribution. Those keep business-relevant information on the back end for the utilities operations. You have ANSI C12, the family that does all the smart metering. And it will define the comms, it will define the meteorology tables, it will define the cybersecurity controls that you need. All of that is available in ANSI C12. Take IEEE C37118. Now you're talking about phasor measurement units and how you control the voltage, current, and phase on a grid. Because by having that data and quickly converging, you know that you have a stable grid. And as those phasors start getting out of whack, you can take proactive steps to avoid it becoming a cascading failure, as we saw in the August 2003. Multi-speak, very important for co-ops in integrating the back end. And also now multi-speak has gone out into the field, and there are devices that actually speak multi-speak. And it was done on the fly, literally, because there was a need in co-ops to automate the back end. Why was there a need? Because the distances between farms was like 7 miles, and you couldn't send a truck around picking up energy reads. So they had to automate. So they used products like TWAX and Hunt, Powerline, very low bandwidth networks to gather the data. But once you're getting the data, you have to integrate. So that's why multi-speak was put together very quickly. People like Bob Saint and Gary McNaughton from NRECA did an amazing job. Gary, I think, is a consultant. But they did an amazing job in putting that standard together. And as I understand it, it's going to become part of the SIM library also. So you see a wide variety. And then TCP, IP, and Ethernet, those are things you already know in the lower layers. Moving along, I'm just showing you, I'm listing them literally to show you in transmission what's relevant. Another one that I was talking about was the Inter-Control Center Protocol. So if you have two control centers, that manage the bulk transmission system, you can have a protocol between them that talk, and that's the ICCP. And TASI-2 has some of the additional security controls in the new version. That's what's called TASI-2. It's a IEC standard 60870-6. I talked about PMU, I talked about field equipment, 61850, and DNP3 secure. Notice it's an IEEE standard now, 1815. And what the 62351 standard did is it fed additional security controls into DNP3 secure. So basically, the DNP user group presented their protocol to the 62351 group of IEC and had them endorse it. So the way 62351 responded by making some additional suggestions and saying, you may look at some additional security controls. So it's coming to very good convergence. Remember, 85% of the infrastructure out there in North America still uses DNP3 secure, still uses serial interfaces to go to most of their remote terminal units and the intelligent electronic devices. So while we're talking smart grid and we want valuation of our companies and all that, and we're excited about it, recognize where the reality is today and be flexible to grow with it. And that's first understanding, identify. Remember how NIST tells you in their cybersecurity framework, first thing you have to do is identify, which means figure out what your ecosystem has. All right, moving right along. The distribution system protocols are pretty straightforward. DNP and 61850 are used in both places, and so is multi-speak for cooperatives. And the SIM for distribution, again, it's an object model, and it's like bins that carry data. They hold data of different things that have business significance. So that's what you keep on the back end. So the idea is you take information from DNP and 61850 and map it into SIM, and then use it amongst your servers on the enterprise IT side and the power systems back end to have a true smart grid. If you don't have that connection, you're not smart. You may be intelligent, but not smart. You may have a lot of data, but don't know what to do with it. DER, again, 61850 has a -7-420, very important standard. Then you have IEEE 1547. That is the interconnect standard for how the distributed resources connect with the electric power system. And then DNP3 Secure also has some features for things like inverters and for wind. And then you have 2.0, which has specs from the Society of Automotive Engineers for everything from the physical connector, J1772, to J2836 and J2847, and on and on and on, that involve the communication between the electric vehicle and the off-board DC charger. Here is the smorgasbord of standards in AMI and home area networks. And I'll just say that today, Zigbee, home plug, and Wi-Fi are the three that are getting the most attention in North America for home area networks. ANSI C12 is there for AMI, for neighborhood area network, into the head end, to the back end, to the MDM. That's all ANSI C12 territory. But in home area networks, we're seeing primarily these three. And particularly for EV, we're seeing more home plug green PHY, because if you're going to send electrons to charge the car, you might as well send the signal on it too. Why rely on another network? That's the argument the Home Plug Alliance has been making, quite successfully, I must say. So I see in the future a hybrid environment, where essentially you'll have a Zigbee meter, you'll have a radio coming to an adapter. That adapter will have multiple outlets for home plug and for Wi-Fi and Zigbee. And that part of the network will be customer managed. And the network between the Zigbee meter and this adapter will be the utility area. Now, in that, maybe they'll put the pool pump and the water heater and the PCT so that the utility can control it. And I think the CPUC, the California Public Utility Commission, has done a remarkable job in showing the three types of home area networks. Utility-centric, customer-centric, and a hybrid. And I recommend that you go to their material and look at those diagrams. Amazing stuff. But There's not going to be any winners in this battle of Zigbee, home plug, and Wi-Fi. They'll all coexist peacefully, hopefully, because there's a business need for all three protocols. In the commercial and industrial space, we have standards like OPC that do a lot of stuff in process control. Now, these are the stealth ones, you know. It takes someone who is involved in the industry to know how big OPC is. But because we in the smart grid community have been so focused on residential, we don't know what OPC is. But OPC is big. And just like Modbus is from a company that is now part of Schneider Electric today, we have LawnWorks that started out with Echelon, but it's an EIA standard, and BACnet, which is an ASHRAE standard. That's the American Society of Heating, Refrigeration, and Automation Engineers, is it? Mm-hmm. And then DALI, which is also part of BACnet, which does lighting control. So these are some of the popular, there are many more, by the way, but I would say that these have big market shares in the commercial and industrial sector. Some of these are application layer. Some of them are application and have some specs for networking. But many of these can run just on a serial interface, like an RS-232 or 485. So you basically have a very primitive application layer with very simple commands, because the types of devices that they're controlling are relatively simple. The things that they ask it to do, turn on, turn off, increase the voltage by this much, decrease it by this much, that's the type of SCADA that's going on for the most part. So for those types of, for that level of sophistication, it's enough to have these standards with a serial interface. But increasingly, we're finding Internet protocol permeating into commercial and industrial, and as a result, we're increasing the ability of these protocols to do more stuff, to be able to control more devices, because an IP network can control more devices. Here's a picture of the Zigbee architecture. Everything you wanted to know about Zigbee, but were afraid to ask. All the left side is the legacy stuff. The right side is this new flavor that has come out with Smart Energy Profile 2.0 that has the Zigbee IP in the middle of the stack and the 802.15.4 at the bottom. When we do certification, like labs like TUV Rhineland will do, they will check all of these layers. It's not just one layer test. It's all the layers to make sure that those specs in those layers are actually met. This is very critical for interoperability. We have seen examples in the utility industry where vendors certified to one utility's territory were not able to work with another utility. And that's just because of the level of interoperability that they tested. If they had gone deeper down to what Marty Burns from Hypertech calls the primitive requirements and match them requirement for requirement, that's where, as they say, the devil is in the details. I believe it. It is in the details. And that's why companies like TU Rhineland exist, so that they can take their magnifying lens and match every spec with what's there in the vendor product, and then show a red flag when there is a mismatch. Here is a residential Zigbee deployment. And again, you see the plethora of devices. Some of these can be run by Wi-Fi, some by Zigbee, and some by home plug. In this case, because it's a Zigbee deployment, everything is Zigbee. But I'm saying that there is nothing to stop the world from coexisting peacefully with the Smart Energy Profile 2.0 as being the canopy that links it all together. Physical media is not necessary to be uniform across all. It's important to have a consistent object model that controls the attributes of the devices. Here's a home plug. Again, you see how the electrical wires carry the data, and then you have a bunch of end devices that it's connected to. One of these devices could be your EV charger. Nothing to stop it. It could be your PCT. So you could have a whole house running on home plug. So what I'm saying is if the whole house can run on Wi-Fi and Zigbee and home plug, a mixed environment can also exist. The next seminar, we're at the end of our technical presentation at this time. The next seminar is going to be on October 10th, and we're going to be providing highlights of the GridStar project. That's the project that I'm now the Director of Strategic Innovations for. I sent out an announcement about that. It's going to be an amazing opportunity for all of you to work with us to do testing of smart grid technologies. Everything from the substation down to the appliances, we can bring them into our microgrid over there and test them to see how your product will work in a larger mosaic. If you're a utility and you want validation of something you're about to deploy, great place to bring it. If you're a vendor and you want to show interoperability and have some visibility with DOE and other agencies, great place to come. If you're an integrator, you want to practice before you deploy, come on over. I mean, if you're a federal agency that develops policy, you want to make sure that the policy that you're writing can actually be supported by the technology. Come give us a test to do. No matter what stakeholder you are, having an unregulated grid that DOE put $5 million, Penn State matched it with another $5 million, built this amazing microgrid, it would be a huge disservice to ignore it. It's there, it's a facility for everyone. And my job is to bring you all over there and do meaningful things. So if you're like TUV Rhineland, you've tested something on the bench level, bring it over there, put it in a commercial setting, and see how it works before you tell your customer it's good to go.
That's our dream. John Lynn and I dreamed many, many years ago to have a multi-node network live.
You go.
That has, you know, at the time we were thinking of each having its own fiber node, right, but wirelessly connected, so you can control timing and things like that, and have like 500 devices, you know, communicating with each other. But we'll see what you can put up at Penn State.
So the ribbon cutting ceremony is on October 30th. I've already sent you all a link. Please register for it. But there'll be a very good presentation by Dave Riley talking about what they did the last 3 years to get it all ready. So I hope you will attend that. And I think I made it in time. There's still 10 minutes for Q&A. Wow. So at this point, what I'll do is I will come down to this point and then see how the questions are. Okay. Yes. So CDMA also is a trick to encode data. Yes, it is. That's carrier detect or collision detect with multiple axes. So multi-axis collision detect, CSMA. And then this is different. This is CDMA. That's multiplexing. That's multiplexing. So you can actually carry much more data with the multiplexing.
With code division. So it's, okay.
Right. You're just breaking it up into smaller.
TDMA is the other one.
Time division multiplexing. Very good. So we have DC low voltage was removed. Sounds good to me. DC in the home was considered an electrocution health risk. Okay. Good to know. Any questions from the people online? I only have 22 people left, but if there are any questions, please post them. I know this was like drinking out of a fire hose, the rate at which I was going, so I apologize for that. But I wanted to do the survey on purpose so that we can get an idea of the landscape, understand where the things are relative to each other, and then we can do deeper dives. So any questions from the audience here in the room? We have about 15 people here. Any questions?
On the OSI stack, where are the most vulnerable cyber attack points?
It's very interesting, but actually I would say in the Phi MAC layer. And it's an area that needs to be hardened. There is a company called Sec Lab Solutions that came out of people working at Electricité de France who are just focused on that. And had we had those types of filters, the Stuxnet virus would not have spread. Because when you have that malware coming, you need it at the bit and byte level to check at the USB port to make sure that the files that are coming into your system are not plagued with those viruses.
Little Johnny.
Yes, exactly. So the best thing to avoid air gap type attacks, in my opinion, is to go to the FIMAC layer and put filters there that are burnt into the code, to the chip, so that they're not something that you can wash the firmware and put new firmware on.
Interesting.
And they should not be network devices.
But that's interesting, because I would think that is what I call, Mike Amadi knows me from before, what I would call a vector attack, like Stuxnet, they are independent from the physical layer.
Yes.
Stuxnet is kind of sitting on top of it, because they don't care how they are transmitted, Remember that most of the stuff, for example, the fast testing, does not cover the data payload, it covers the protocols that are sitting on top of it, and that's the danger. I know what you're saying. So you will kind of want to put like a check and balance into the file layer so it doesn't get anywhere from there on out. Interesting. Yeah.
Yes, and there are data diodes available, and as I mentioned, the company SecLab Solution is providing that now, and this is very important for the nuclear industry, where the different levels of security based on whether you're in the radiation portion of the nuclear reactor, the non-radiation portion, there are 4 levels of security in the nuclear power plant. And you need something like a data diode so that you can't do exfiltration of data. Only acknowledgements go back that are authorized. And that's why it's called a data diode. So data can come in from outside sources, of course with the filter, but only specific acknowledgements will go out and nothing else. And only devices at the hardware level can actually do that effectively.
Interesting. Now I heard about that.
So look into that. Of course, the Internet protocol continues to have vulnerabilities, and we are working on that. But a lot of those can be dealt with bump-in-the-wire type solutions on a perimeter, or you can have more universal authentication schemes like LDAP and things like that, and bring it. There's a company called Blackridge that will put TCP in the sequence numbers. They'll put a token. That authentication token from the transmission control protocol. So those types of things we can do to make it more resilient. But I think the answer, Gary, is all layers are important, because any layer you ignore will become potential for the hacker to compromise. So you need to have overall situational awareness, have a very good understanding of what normal procedure is, so you know what an anomaly is. I think a lot of times we don't know what an anomaly is, because we're too busy, as I said, drinking from the fire hose. And so you need hyper-quiet networks, you need to segment your network, and you need to only move data on a need-to-know basis. Don't do broadcast storms. Limit design your network so that traffic only moves when it's needed to whom it needs to go to. And by quieting down the network like that, you will see a hacker like a sore thumb, especially these that compromise trusted systems and then attack. Their behaviors always violate some law of normal operations.
But what you're proposing is kind of diametrical what is happening now,
Yes.
You're proposing a new type of Internet here, because...
But I'm talking about enterprise networks.
Oh, okay.
No, the Internet will remain the wild, wild west. And I think it's important to know what to trust and what not to trust by having a good filter. And you also have to know when these phishing schemes and things like that are happening. So proactively, you can block them from attacking you, especially distributed denial of service type attacks. There's a preparatory work that occurs. And if you can find that, it's very good. So we'll have another talk in which we'll talk cybersecurity and what's important. But I think a few key takeaways from this is that, one, electricity has a way of flowing down a wire. And I showed you. I didn't show you much smarts today. Why we need the smarts is when you have intermittent sources of energy that are being introduced from multiple points of ingress. It creates a two-way energy flow system. And to stabilize that requires active control. And that is why you need the protocols to control it. Otherwise, if you had an excess of electricity and a bunch of loads downstream, just normal Ohm's law and Kirchhoff's laws are enough. As long as you have a conductor carrying the electricity, it'll carry it to the load. And that's what I showed you for the bulk of this talk. But I slowly transitioned you to electronics and data communication because in future I'm going to show you why these are important to control field equipment when you have entropy coming in from systems like solar and wind, especially. Because they're very, very intermittent. They can suddenly drop. And as long as it's a small percentage of the overall mix, no problem. But as they get bigger and bigger, you either have to have storage, you all have to have comprehensive demand response, or you have to have dynamic control to do control voltage reduction.
I would think that we can learn a lot from the financial industry because they have learned to do one thing. It's called statistical arbitrage. You know, these are neural networks that they employ, or neural-like networks that they employ to arbitrate, as the name implies, to arbitrate financial numbers, money.
Yes.
But what we arbitrage is actually energy, right?
Right.
But the mathematical models that they have developed, you know, they are very applicable about what we have here. And in the end, the two worlds need to merge in order to make renewable energy successful. Because in the end, what we need to arbitrage is demand, supply, storage, and distribution.
Sure. Great. So we have reached the end of our time. I'll entertain one more question.
Yes, you know, there has been studies at Stanford showing how renewables can take over 100% of the energy and totally eliminate all fossil fuels.
Yes, I like it. I also like how we're liberalizing our laws with marijuana consumption also, because you have to be in a certain state of being high in order to believe that and also have some notion of an understanding of physics. I know that I have personally been part of microgrid projects where we have done 100% penetration of renewable energy, but it required a storage that had a power equal to the power of the renewable energy.
Well, what if it's 25%?
I have absolutely no issue with any points up to 100%. What I'm saying is that these types of statements have business behind them much more than they do technology and engineering.
Well, the California Energy Commission is requiring utilities to put up battery grid storage of, I think it's
yes, yes, and I think this is great because
I think it's 1.3 gigawatts or something like that.
Yeah, the issue is that the policy is driving us towards greater and greater renewable energy on the grid, no doubt about it. But if you look at it, the goals are actually conservative. I mean, they're not that aggressive. And they include all types of renewable energy, not just solar and wind. So when you look at it that way, it's reasonable. But when you have entities making observations like this, where we're sitting, you know, on a beachhead right now, and they're talking about miles over there, I feel it's a little irresponsible, because tomorrow if some policymaker starts believing that and they start saying, okay, well, we're going to go 100%, what it will do to the stability and security of our nation, I worry about that. So that's why I was making that comment.
Why do you take that position? Germany has 4 to 5 times the renewables penetration that we have in the United
Germany
States.
is a country that's running like a microgrid. When they want electricity, they go get nuclear power from France, or they get it from hydro plants in Norway and Sweden. But they claim that they're this % renewable.
What Germany is selling excess renewable energy,
on
or
certain times of the day.
France is 80% nuclear. And France doesn't get enough energy, and so they purchase it from Germany. So you know, that's a fact. So you're saying is
I actually know. Good, Michael.
Matthias is German, and he will tell you about how Germany works. What I want to do is I want to bring this discussion to an end, and then we could have this offline. And the reason is because there are people on the call who, it's after 5 o'clock on the East Coast, so I have to be respectful to them. But I do want to continue this discussion. So at this time, I would like to thank the people online. And our next presentation is going to be on October the 10th, as I mentioned. It'll be a Thursday. I'll send out the invite. I appreciate your participation. The presentation and the recording is going to go out to all of you in the next couple of days. And once again, thank you so much for participating, and goodbye.